size different from the parent ion. Okay, and then here one green dot I have shown. Green dot is some other foreign atom sitting in a place where it should not be sitting. There is no lattice position there, but it is coming and sitting in a hole there. That is why it is called an interstitial. Okay, this is how a real material will look. A real conductor will have this picture. It will have lattices, and then there will be free electrons, and then there will be impurities sitting in the wrong places, and then there will be interstitials. Okay, now what happens? I told you in the last class that these electrons will be in random motion when you are not applying an electron, when you are not applying a field. But the minute you are going to apply a field, along with the random motion, there will also be a drift happening in a direction opposite to the direction of the applied field, and this average velocity with which it is drifting is called the drift speed. Okay, now the question is, what causes resistance in metals? You all know that when you heat a metal, resistance of the metal goes up, right? So what is resistance first of all because of? Now please remember, you're seeing that this electron, every time it is hitting against a lattice or hitting against an impurity or hitting against an interstitial, it's losing all its energy and its direction is changing. So the first reason for the resistance is this interaction, That is the first point you have to remember. Next thing is, you must have studied in your intermediate that electrons are waves. So please remember, when they are going to move through a structure that is uniform, there is no collision happening. But just imagine if in the wrong place there is going to be some other atom sitting, then there is a collision. Okay, so first of all, a material which is pure should not have as many collisions as in the case of a material that is impure. So impurity atoms are one of the reasons for resistance. Next thing is, when the lattice is going to hit against the electron. Now the question is, why is it going to hit? That is a question. Please remember, I'm going to discuss something very important. What happens is, I told you, because of thermal energy, these electron fellows are free, so they are able to run around. Okay, random motion, thermal motion. But what is happening to the lattices? The lattices are fixed to their position. The positive ions are fixed to their position. But remember that they are not going to sit still. They will start vibrating about their position. I hope this point is clear. Is Kiranmai back? Kiranmai, are you back in the class?
Yes.
Yeah. So what happens is positive ions, these lattices, will start vibrating about the mean position. Why are they vibrating? They are vibrating because there is energy. You studied in last semester in mechanics that you need energy for simple harmonic motion. Similarly, here also, because of the thermal energy, they start vibrating. Each of them will be vibrating about their mean position. Okay, so now when the temperature goes up, larger will be the vibration because larger energy. So larger will be the vibration. So what happens is, there will be a mismatch happening between this regularity because of the vibration. Therefore, what happens is, there is a greater chance that the electron will interact with the lattice or hit against the lattice. Okay, so as you raise the temperature, larger will be the collisions, larger will be the resistance to the flow of free electrons. Okay, so please read this now, it will make sense. What causes resistance in metals? The viscous effect, viscosity. Remember, these electrons are like, flowing through some liquid. Okay, so the viscous effect of scattering. Scattering is when it hits and changes direction. That's called scattering. The viscous effect of scattering of the free electrons by the lattice imperfections. So what is this lattice imperfection? Lattice imperfection may be a missing atom or a wrong fellow sitting there, or sometimes what happens is, there is a vacancy. The atom is not even there. So what happens is, there is a discontinuity in that regular arrangement. Okay, then there is a greater chance for lattice interacting with the electron, or there is a collision. Then another reason can be impurity atoms. Like the other day I talked about carbon. Carbon is a very small atom. It can go and sit in an interstitial. Okay. Or in the case of iron, maybe some other ferromagnetic material can go and sit. Okay. So, and then finally, lattice vibration, which I just explained. So these are all the reasons why there can be resistance. And now you can also understand why the resistance of a metal increases when you raise the temperature. Because when you raise the temperature, lattice vibration increases, thereby the chances of collision between the free electron and the lattice increases. Therefore, there is more resistance. Okay. And another thing is, if you add more impurities also, you can achieve the same thing. So the next question is, how can the resistance of a metal be increased? This point is very interesting. How can the resistance be increased in a metal? Just now we have seen raising temperature. If you raise the temperature of the material, increase lattice vibration. Therefore, more collisions, more resistance. Second thing is adding impurities. When you add impurities, then also what happens is the wrong atom sitting in the wrong place spoil the regularity. Therefore, the wave is not able to pass without colliding. Therefore, there is more resistance. And then finally, you can do something to actually increase the resistance. For that, I normally give the students one example. These days, most of you use your turkey towels to dry your hair. But then if you look at one generation back and all, people would use pure cotton thin towels to dry hair. Have you seen this towel that I'm talking about?
Yes.
Right. So if you take one such towel and then hold it up in the air against light, okay, when it is new, you will find that all these threads are equispaced. All the threads are equispaced. So that is like a pure, perfect lattice. There is no perfect lattice in real life, in real metal, but I'm saying what is the best approximation is taking a new towel and holding up against light. You will see that all the threads are equispaced. So it is like a perfect lattice. Now take the same towel, put it in water and squeeze it dry. Put it in water and squeeze it dry and then hold it up against light. What do you expect you will see? Use your common sense. I take this new towel, I put it in water and then, I wring so that the water goes off and then show it against light again. What do you think I will now see? How will the picture be different?
The threads will not be equispaced.
Very good. The threads will not be equispaced. You will find that at some places the threads are closer, some places they are wider. So that is like your lattice imperfection. Okay, so how did we achieve this in the case of the towel? By mechanically straining the towel. By mechanically straining the towel, you did it. Same thing can be done in the case of a metal also. If you take a piece of metal and then strain it severely, straining means what? Twist it severely, then what happens is you can actually spoil the lattice perfection. You can introduce lattice imperfection, just as I told in the case of the towel. Okay, then what happens is your resistance will go up. I'm sure many of you have noticed it. In certain electrical connections in your house, certain devices are there. You will find that when the wire is new, when the connector wire is new, there is no heating. But with use, what happens is you will start finding heating effect. Have you noticed that? Even in the plug, for example, the plug you are putting inside the socket, in the initial days, there is no heat. Everything will be going fine. After a few days, even your charger you take, after some time, you will find that there is heat. Have you noticed that?
Yes.
Right. That is happening simply because, because of continuous use, you have actually strained that part of the metal and you have actually introduced imperfection, lattice imperfection. And because of that, there is a higher resistance. So there is a resistance to the flow of current. And whenever there is a resistance to a flow of current, that is when you find heat. There is energy, but that energy is not in the form of electricity. It is getting converted in the form of heat. Okay, so you can just conclude that any metal You can play with the resistance of the metal by three ways. One, raise the temperature. Second, add impurities or alloy the metal. Third is strain the metal. By these three ways, you can actually increase the resistance. Are these points clear, guys?
Yes, ma'am.
Okay. $28, 33 people. Very nice. And all these fellows, see, guys are going to write examinations even without studying. You are all thinking you are lucky right now, but tomorrow when you go to the job market, what is going to happen to you all? I'm worried. Okay. Now let's quickly see one problem. Before we see that problem, I want you to go to one formula that we have used yesterday. Resistivity is equal to M by N E square tau. This is what I did when I was going out of the class yesterday. Tau is called the mean free time. Mean free time is the time between, average time between two collisions. Average time between two collisions. Okay. And N is the number density. M is the charge of an electron. E is the charge of the electron. Okay. Now using this, we have to do this problem. What is the problem? What is the mean free time between collisions for conduction electrons in copper? In copper. So this is your formula. This is your formula. Okay. Mass of an electron, you can always, you know it, 9.11 into 10 to the power of minus 31 kg. It doesn't depend on which is that metal. But N depends on the metal. N, we have done in the previous problem, we found out N. It was 8.49 into 10 to the power of 28 electrons per meter cube. Then charge of electron is 1.6 into 10 to the power of minus 19. So square it because we have E square. And finally, the resistivity is 1.69 into 10 to the power of minus 8 ohm meter. Where is it coming from? It is also coming from the table. This part is coming from your table. Okay, table of constants for different material. It comes from there. In an examination, we will give that value to you. So if you calculate what is the mean free time, you will get it is 2.48 into 10 to the power of minus 14 seconds. Can you imagine what is 10 to the power of minus 14 seconds? 10 to the power of minus 9 seconds is nanosecond. 10 to the power of minus 14 seconds means, just imagine, that is a small duration that the electron is able to get for accelerating because of the field. Within that short time, one more collision, again loses energy. Again it accelerates, again loses energy. So just imagine what little time it is able to get for acceleration between two collisions. Okay. Next, you have done this. Basically, these kind of problems, when you do know, you get a feel for why the drift velocity is so small. You are able to see how fast they are losing energy. Next, you are also asked to find out what is the mean free time, mean free path. What is mean free path? Mean free path is the distance between two successive collisions. Distance that electron can move between two successive collisions. Or you know that distance between two collisions divided by the time between two collisions is going to be the, it's going to be the velocity, average velocity. And you know that average velocity is actually 10 to the power of 6 meter per second. Please guys, I hope you're noticing what I'm writing here. Lambda divided by, I told you what is lambda. Lambda is the time that the electron is going to get between two successive collisions. Okay. And the time taken is tau. And what did I say? Between two collisions, it is in random motion. It is having a velocity 10 to the power of 6 meter per second. Now, some of you there may ask me, ma'am, when there is an electric field, there is also a drift velocity. But look at the drift velocity value. Drift velocity value is very, very small. Very, very small when compared to the thermal average velocity. Therefore, you can just neglect that part and only consider the thermal velocity. Did you understand this step, guys?
Yes.
Right. Okay. Between two collision, if you have applied a field, this random thermal movement, average thermal velocity is also there, along with a small drift. But then that drift is negligible, so you can neglect it. Okay, therefore, you can talk about only this, and it's around 10 to the power of 6 meter per second we have seen yesterday. Therefore, you calculate your lambda and see lambda is 4 into 10 to the power of minus 8 meters or 40 nanometers. Anyone here? See, every number here has a significance. Do any of you know what will be the typical distance between two lattice points in a metal? I'm sure you studied in chemistry and all. A parameter, B parameter, C parameter. Have you studied all this? Face-centered cube, BCC. You studied all this, right?
Yes, ma'am.
Right. So you must have seen that the distance between two atoms can be of the order of nanometer, 1 or 2 nanometer. That will be the typical distance. So that means what it shows is an electron is able to cross, let us say, 5, 6 lattice points before it suffers a collision. But then, because of the collision, it moves back in other direction. Therefore, effectively, it is able to move only very slowly. Okay, you should have some sense for these kind of numbers. So one of the number that I wanted you all to remember is N for a metal. N will be of the order of 10 to the power of 28. Next thing that you should know is typically what is the order of the time between two collisions. It will be around 10 to the power of minus 14. And how much distance can it travel? It can travel some tens of nanometers. You're not expected to remember every value, but then the order of these numbers you should. And similarly, what is the velocity with which there is a thermal motion? It's of the order of 10 to the power of 6 meter per second. Similarly, what is typically the value of the drift velocity? It is a few centimeters per hour. Okay, you should have a feel for all these numbers. Then finally, look at this. Oh, in fact, it is much more than what I thought. I said tens of lattice points it can move, I said. He says it's about 150 times the distance between the nearest neighbors in a copper lattice. So if you have one atom here, 150th atom is here, it is able to move that kind of distance, but then because it is bouncing back every time after a collision, the drift velocity is very, very small. Okay? And another thing that you should remember is we use the word collision. We use the word collision in a very loose sense. We are talking about a collision between an electron and the lattice or the positive ion. But then in reality, it is not a collision. You actually need quantum mechanics to understand that it is not really a collision. Okay? And then he also says that this mean free path, which you just saw, is 10 to the power of minus 14 meters. I mean, 10 to the power of, how much was that? 10 to the power of minus 8 meters for copper. In some materials, it can even be as high as 10 centimeters. It can even be as high as 10 centimeters. And when will it be 10 centimeters? It can become 10 centimeters when the material is as close as possible to a pure metal. A pure metal, you can actually purify metal and remove all the impurities. If you purify the metal and remove a lot of impurities, and then if you cool it down to 0 Kelvin, then what happens is the lattices will not have energy to vibrate. They are going to sit still in their places, and then there is no impurity also. In such conditions, you can't remove impurity completely, but the impurity will be less. In such conditions, what happens is, it is able to travel to even distances as great as 10 centimeters before a collision. That means in these cases, the resistance will be very, very small. Okay, so this is actually a classical picture of resistance that we have given. Quantum mechanical treatment will be different, which is out of your syllabus. Okay, now that we have completed this, let me quickly now move to another class of materials called dielectrics or insulators. Let us see what happens to a dielectric in an electric field. Before that, I want to quickly take you to the old picture that we did 2 days back. We have seen what happens when you put a piece of metal in a uniform electric field. We found that the electrons will flow against the electric field, go and deposit on the top surface, and at the bottom surface there is an effective positive charge, and they behave like two plates, a positive charge and a negative charge plate. So there is a field because of this, and this field is called the induced field or the polarization field. And this field will be exactly equal and opposite to E naught that you applied. Therefore, inside the material, the electric field is zero. This is electrostatic equilibrium in the case of a metal or a conductor. Now, keeping this in mind, let us go to a dielectric. Okay, so let's see what happens in the case of a dielectric. So before we get there, we have to first of all talk about types of dielectrics. Dielectrics can be classified into polar and non-polar dielectrics. The picture given here is non-polar. The picture given here is of non-polar. You can see that when the electric field is zero, when there is no electric field, you look at the picture, you're seeing the nucleus, and then around it, the pink shadow is the electron cloud. And if you see the symmetry, you're finding that there is a great symmetry between the two, or the center of the nucleus and the center of the electron cloud will coincide. Therefore, polarization or dipole moment is zero. Okay? Now, let us apply an electric field. When you apply an electric field, like what is given here, what will happen to the positive charges? The positive charges will experience a force F is equal to Q into E naught in the direction of the field. In the direction of the field. So the positive cloud will get shifted to the right. Similarly, the negative charge will start getting shifted to the left. Okay. Now what will happen is, if you try to see the center of the positive cloud and then the positive and the negative charge and treat them as points, you will find that the negative charge point is here and the positive is here. There is a displacement of the centers of the two because of the applied field. Or in other words, you are getting a minus Q and a plus Q separated by a distance D. Now what is this called? A plus Q and a minus Q separated by a distance D. What is this called?
Dipole.
Dipole. This is called a dipole. But this is not a permanent dipole. This dipole got induced. Who induced it? The electric field that you applied induced it. Okay, so these class of materials which do not have permanent dipoles but which get induced dipole when you apply an electric field, these kind of materials are called non-polar dielectrics. They are called non-polar dielectrics. So if I take a block of material and then find out what is going to be the dipole moment, you will find that the net dipole moment, please remember dipole is a vector. So what happens is, in the state when electric field is zero, you find that there is no dipole itself. Therefore, the net dipole moment is zero. But the minute you apply an electric field, then what happens is, you will find that the dipole is formed and the dipoles are going to be aligning almost parallel to the electric field. I'm saying almost parallel to the electric field because there is also something called thermal energy. The thermal energy always tries to create a chaos, like what happened with free electrons. So what happens is the thermal energy tries to vibrate these dipoles. So what happens is all of them will not align parallel to the electric field. This you studied in chapter number 26. A dipole always wants to orient itself in the direction of the electric field. Okay, that perfectly will not happen because of the thermal effect. But then almost an alignment will be there. Therefore, the net dipole moment, if you find out, will not be equal to zero. There is a net dipole moment. This is what happens in the case of non-polar insulators or dielectrics. Okay. Now let us go to the next class of dielectrics. These are called polar. These are called polar. And what are polar dielectrics? Polar dielectrics will have permanent dipoles. Best example would be water. The best example will be H2O. There is a molecule here. Okay, there is a negative charge here and a net positive charge on this side separated by a distance. This is a permanent dipole. Okay, now these kind of class of materials are called polar dielectrics. Okay, so let's give a picture of how a polar dielectric will look. Look at this. When the electric field applied is zero, what happens is each molecule or atom behaves like a dipole, but look at their orientation. They are all randomly oriented. They are randomly oriented. So if you take a block of the material and get the vector sum of all these dipoles, you will get zero. You will get zero or a small value maybe. Are you following what I'm saying? Think of random vectors in different direction. If you put them together and get the vector sum will be zero or close to zero because they are all randomly oriented. Next, the next picture, you're going to apply an electric field. You're going to apply an electric field and you're going to apply an electric field in this direction. So what happens to these dipoles? The dipoles will try to align themselves. Thermal effect is trying to spoil it, but then the electric field that you have applied will try to align. So look at this, the positive end tries to go in this direction and the negative in the opposite direction. So now if you try to find the vector sum of all the dipole moments here, the vector sum will certainly not be equal to zero. There is a net dipole moment for the block of the material. So in the first case, dipole effect happened because of induced dipole effect. Initially there was no dipole. But in the second picture, in polar materials, what happens? There are dipoles. But then it is not oriented. They are all random. By applying an electric field, you are giving a torque and aligning. And thereby, you are able to get a net dipole moment for a block of metal. And please remember, larger the electric field you are going to apply, larger will be the energy with which it is able to overcome the thermal effects and it will orient better. Orienting better means larger will be the dipole moment. Is it understood, guys?
Ma'am?
Yeah.
In the case of non-polar dielectrics, the moment I remove the electric field, will it again become a single entity?
Yes, it will become a single entity. That's why we say it is not having permanent dipoles. Permanent dipoles will not be there. Induced dipole will appear whenever you are applying an electric field. When you remove the electric field, it goes to zero.
Okay, ma'am.
Okay? Yeah. Now, within polar or within permanent also, there are two classifications. Okay? Within permanent or within polar also, there are two classifications. One will be called paraelectric, and the other is called ferroelectric. Ferroelectrics have lot of application, lot of research goes on in ferroelectric. Okay, so paraelectric and ferroelectric. Let us see what is the difference. Paraelectric means in the absence of electric field, the dipoles are so randomly oriented that the vector sum will be zero. The vector sum will be zero in the absence of an electric field because they are completely random. Permanent dipoles are there, but they are all randomly oriented. When you apply the electric field, yes, there is an orientation. These are called paraelectric. Next, let us see what are ferroelectric. Ferroelectrics, what happens is, they are random all right. They will be random all right. But even within this random, there will be a small order. There will be a small order. So that when you try to get the vector sum will not be zero. The vector sum of the dipole moments will not be equal to zero. Okay, or in other words, we can simply say that, I'll go back to the picture and say, in the case of ferroelectrics, what happens is, hey, do you remember in chapter number 26, we have seen each dipole becomes a source of electric field. Do you remember there can be an electric field because of a dipole? You remember that? On the perpendicular bisector, you took a point and found the electric field. So that means a dipole itself can be a source of electric field. Okay. And you also saw in the same chapter that a dipole can get if affected by an external electric field. A dipole can be a source of electric field. A dipole can also be affected by an external electric field. It tries to orient. So, this class of materials called ferroelectrics, what happens is, they are strong sources of electric field. They are so strong sources of the electric field that two neighboring dipoles can also affect each other. They can also affect each other. Are you following what I'm saying? The dipole moment is going to be different for different class of materials. Okay. Now, in the case of ferroelectrics, what happens is the dipole moment is high. Therefore, each dipole becomes a strong source of electric field. A strong source of electric field. So what happens is they can actually influence each other. Small influence, but they can influence each other. And there will be a small amount of alignment happening. One dipole behaves like a source, the other behaves like a like the dipole which is getting affected. Okay, so this class of materials in which you're going to find a dipole moment even in the absence of applied electric fields. Such materials are called ferroelectrics. Ferroelectrics. Now, when you apply an electric field, you get a large dipole moment. You get a very large dipole moment. A great degree of alignment will be there, parallel to the applied field. And this class of material has got a lot of applications in energy storage, in your sensor applications. In so many places, there are applications of ferroelectrics. They are a very important class of materials. Now, I'm going to define a new quantity called polarization. Polarization is, I told you, you can add the dipole moment for each of the atom present inside a block of material. So if you add up everything and divide by the volume of the metal, volume of the dielectric, then what you get is called the polarization vector. So what is polarization? Polarization is the net dipole moment per unit volume of the material. Okay, now that you have understood that there are polar dielectrics, non-polar dielectrics, and then how they are different from each other. Then within polar, you saw paraelectric, ferroelectric. All this you have seen. Now let us see what happens if you take a rectangular block of dielectric and put it in an electric field. Put it in an electric field. So here is a, please understand properly. Okay, so this is your first picture. You're going to take it and put it in an electric field. When you put it in an electric field, irrespective of whether it is polar or non-polar, irrespective of whether it is non-polar or polar. If it is polar, the already existing dipole will align in the direction of the applied electric field. You can see the positive end is looking down, negative end is at the top. If it is non-polar, what happens? The shift of the electron cloud and the positive cloud also will result in oriented dipoles, oriented induced dipoles. In any case, there is a dipole formation. There is an orientation, so there is a polarization. Okay, now you just look at the top surface. What is the charge that you're finding on the top surface? Look at the picture here and tell me. You're seeing that finally getting an induced negative charge formation on one surface, and look at the bottom surface, you're getting a net positive equal amount of positive charge on the opposite surface. This is similar to what happened in the case of a conductor, but in conductor, how did that happen? Anyone remembers? In the case of conductors, it happened because of actual motion of electrons. The actual motion of electrons moving against the electric field and deficiency of electrons in the other phase, so it is positive. So the actual motion of charges, it happened there. Whereas here, there is no actual motion of charges. There are no mobile free electrons. But just by the orientation of the already existing dipole or by induced dipole formation, you are able to get induced charges on the two faces of the material, or there is a polarization. I hope you are able to see the difference between the two situations. Okay, now look at this. These two will behave like two sheets of charge of opposite sign, which means they will set up their own electric field. And this electric field that it sets up is called the induced field. And look at the direction of the induced field. The induced field is opposite in direction to the applied field. Applied field is this, and the induced field is in a direction opposite to the applied field. Here stops the similarity between conductor and dielectric. In the case of conductor, E naught magnitude was equal to E prime. E naught was equal to E prime. But in the case of a dielectric, you will find that E naught will be greater than E prime. E naught will be greater than E prime. E prime will be small because there are no mobile charges. Whatever polarization you're getting is simply because of only orientation. So as a result, what happens is, look at this, the net field inside the material will be the vector sum of both these fields. You can see that they are in opposite directions. Therefore, which is greater? E naught is greater than E prime. Therefore, the net field inside the material, the net field E inside the material is parallel to E naught. It is parallel to E naught, but then smaller than E naught. It will be parallel to E naught, but then smaller than E naught. In the case of conductors, net field inside was 0. But in the case of dielectrics, net field is non-zero, but it is smaller than the applied field. Okay, so now what do you conclude from all this? The conclusion is that when you place an insulator or a dielectric in an electric field, there will be induced surface charges formed. And what is the job of these induced charges? Their job will be to weaken the field inside. It weakens the field inside. The field inside will be less than the applied field. Guys, is this clear? Let me see if anybody is there at all. 36 people are there, but nobody is even talking. Either Akshara will talk or Kiran Bhai will talk. Maruti girl, so you understood. Okay. So now, let us see the consequence of this. Now we have a class of materials called linear dielectrics. Linear means straight line, right? Straight line graph you should get. So linear materials. What are linear materials? Linear materials are those materials in which the induced field is directly proportional to the applied field. That's not difficult for you to understand. The separation or the orientation for polar or the separation for induced dipoles will be more if you're going to apply a larger field. So larger the field you're applying, larger will be the induced field. Okay, and from this it also turns out that therefore you can see that the net field also will be directly proportional to the applied field. The net field that you're getting is going to be directly proportional to the applied field, or you can put a proportionality constant. This proportionality constant is 1 by kappa E. 1 by kappa E. It's not K, it is kappa. Okay, it's kappa E, and this kappa E is called the dielectric constant of the material. You will see dielectric constant only for dielectrics or insulators. That's why it's called the dielectric constant. Kappa E is the dielectric constant of the dielectric. Okay, I'm sure you've all heard of dielectric constant. There is also another formula for dielectric constant. So from here, what do you get is dielectric constant. So dielectric constant kappa E can be written as E naught divided by E. From here you're getting kappa E equal to E naught divided by E. Which is greater? E naught or E?
E naught.
E naught is greater. Since E naught is greater than E, that would imply that kappa E will be greater than or equal to 1. Kappa E will be greater than or equal to 1. When will it be 1? It will be 1 for free space. It will be 1 for free space. And for all other dielectrics, it will be greater than 1. See, I am deliberately writing this because, you should have an understanding. Many times in an examination, is it E naught by E? Is it E by E naught? Then immediately you think of dielectric constant. Dielectric constant values have to be 1 or greater than 1. Therefore, the formula is this. Okay, if you are able to connect ideas like this, learning becomes easy. Okay, now let's go to the next part. So it is these induced charges, no actual flow of charges, just because of orientation or formation of dipoles, you're getting induced charges on the two surfaces of a dielectric. And it is these induced charges which are responsible for the attraction of a charged body and an uncharged insulator. For example, paper bits getting attracted to a charged cone. Paper bits getting attracted to a charged cone. The charge comb becomes the source of the electric field. The charge comb becomes the source of the electric field. And what is going to happen to the bits of paper? The bits of paper will have, paper is a dielectric, the bits of paper will start, if I say that the field is in this direction, the bits of paper will behave in such a way that the positive induced charge will be on this side, negative induced charge will be on the surface. Positive here and negative here. Now, which side is closer to the comb? Which side is closer to the comb? If I say that the comb is positively charged, then the electric field is going to be in this direction. So which side is closer to the comb? Is it the positive or the negative side? Negative side. Therefore, the attraction will dominate over the repulsion because of the negative side. That's how paper bits get attracted to a charged comb. Okay. Now, I also told you that if I'm talking of dipole formation, I also told you that in induced dipole formation, I told you that larger the electric field that you are applying, larger will be the separation between the electron cloud and the positive charge. Okay, so this is positive, this is negative, or D is going to depend on the separation. The separation D is going to depend on A naught. And D is going to be related to P. P is equal to QD. So larger will be the polarization when you apply larger field. Now what happens when you keep on increasing the field? When you keep on increasing the field, they will not go like this infinitely away from each other. At some stage what happens is single electrons will get sufficient energy to simply get knocked out. And what remains will be the positive ion. Okay, so when each atom is going to give out electrons like this, then you are having a huge amount of electrons. When something is having a huge number of free electrons, what is that material called? That material is a conductor. Or the dielectric has become a conductor when you apply a sufficiently large electric field, so large that it is going to exceed the dielectric strength. Does anyone remember what is dielectric strength? I mentioned that in the first class. Dielectric strength is the strength of the given atom to withstand applied electric field. It can only take so much electric field. If you cross that, then what happens? The electron breaks loose. The dielectric is no longer a dielectric. It breaks down. Okay, this is called an insulator breakdown. And once it breaks down, it behaves like a conductor. Do anybody remember some examples that I gave for breakdown of insulator? Anyone? 2 times I gave this example in the class. In 2 classes, I gave the example. Anyone remembers? Loudly. Air. I talked about lightning. Air is otherwise an insulator. But then when there is a lightning discharge, what happens? The different atoms in the air, nitrogen, oxygen, all these fellows, they just get ionized. And then you can see that there is a path for the flow of electrons. That's how lightning strikes the earth. And that you see as light. Okay, that's actually the path of the electron through the cloud. Okay, and the conditions are conducive when there is more moisture, like in the case of a rainy season, when the cloud is laden with moisture. Okay, so now let's do the last 5 minutes of the class. Okay, with this chapter is getting over. So here you are given two circular conducting plates. Two circular conducting plates of area, or the radii is not given directly, radius is given. Okay, therefore area is pi r square. The radius is given as 4.2 centimeters, or radius is 4.2 into 10 to the power of minus 2 meters. And the separation between them is 0.65 centimeters, or 0.65 into 10 to the power of minus 2 meter. Okay. Now, they carry equal and opposite charges. Let us say one is positively charged and the other is negatively charged. And the sigma plus is equal to sigma minus equal to modulus of sigma. Sigma means, I'm not talking of conductivity here, please. Sigma means surface charge density. Surface charge density is 2.88 into 10 to the power of minus 7 coulomb per meter square. One is positively charged, the other is negatively charged. And additionally, what you're going to do is, first of all, I want you to do this. What will be the field between the two plates? What will be the field between the two plates, and what is the direction of the field? Anyone? Between these two plates, what will be the kind of field that will be there? Anyone? We have done this. For a metal, we did the same problem at the beginning of the chapter. There will be uniform field. There will be uniform field, let's call it E naught, given by sigma plus by 2 epsilon naught because of positive plate, plus sigma minus by 2 epsilon naught because of the negative plate. So that becomes sigma by epsilon naught. Okay, what is sigma? Sigma is given as 2.88 into 10 to the power of minus 7 divided by epsilon naught is 8.85 into 10 to the power of minus 12. Okay, so you get E naught. Is this clear, guys? How to find out the electric field? Because of the two plates, then they are conductors. Okay, now the problem doesn't end here. The problem says that now the space between these plates, the space between the plates is going to be filled by a dielectric called Pyrex. Is going to be filled by a dielectric called Pyrex with dielectric constant 4.7. So let us fill it. So the space here is going to be filled by Pyrex. Pyrex with dielectric constant kappa E equal to 4.7. So this is equivalent of putting a block of dielectric in a uniform external field. Are you able to see the connection? This is the same as putting a block of dielectric in a uniform external field E naught. E naught is given by the two conducting plates which are charged. Now you have put the block, the dielectric block in between them. Okay. So now let me draw another picture. So I think I will create a new page and do it. Or let me just keep it here and do it. Okay. So now what did I first say? There is going to be an E naught that was created because of the two plates. An E naught value is this. Okay. Now what have you done? You have put your dielectric, what is the color I used there? I used blue. Okay. So let me use the blue again. I have put a rectangular block here. Okay. Now what will happen within this rectangular block? Quickly tell me, recall what I just said a few minutes back and tell me what will happen.
Electric field will be induced in the block.
Yeah. Whether it is permanent dipole, a polar or non-polar, there will be a induced pole effect. And what will be the charge on this right side face? What will be the charge? It will be positive. Positive charge always goes in the direction of the field. That's why positive. And this side will be negative. So these charges are called sigma induced. I'm saying sigma induced. Q induced is what you have to say. I'm saying sigma induced because I'm talking about charge distribution on the two surfaces. Okay. Now, what you have to do is, let's go back to that problem. Let's go back to the question and see. Find the electric field in the glass. Find the net electric field in the glass. What do you expect the electric field in the glass will be? Will it be more than applied or less than applied?
Less than applied.
Less than applied. So what is going to reduce the field? The field is going to be reduced by the induced electric field. By the induced electric field E prime. And look at the direct. Sorry, I made a mistake here. What is the mistake? Can anyone say? What is the mistake I made? Direction. Direction. Very good. So the direction of the induced electric field will be this. This will be the direction of the induced electric field E prime. And it will be less than E naught. E naught is the applied field. So that's E naught. Okay. So now I want the net field. So to find out net field, what should I do? I already know there is a relationship between E naught and E. And what will be the direction of E? I will use green for that. What is the direction of E? What will be the net field? Net field, yeah, net field is the vector sum of these two. So that will be in the direction of E naught, but a small arrow. It will be a small arrow. The value will be small. So this will be E. Okay. And I already know the relationship between E naught and E. I've seen that E naught by E is equal to kappa E. I know kappa E, it is already given for my sample, it is 4.7. I know my E naught also. So therefore, I get my E. E is going to be E naught by kappa. E naught I calculated from the previous page. It is 3.25 into 10 to the power of 4. So that divided by 4.7, okay, gives you the net electric field. The net electric field is 6.9 into 10 to the power of 3 Newton per coulomb. Look at this. It is smaller than the applied field. It is smaller than the applied field. So the job of the dielectric was to reduce the effective field inside. Okay, now the next part of the question is, I want to find out what is the induced field. I want to find out what is the induced field. What will be the induced field? I know E naught, I know the net field. So what will be the induced field? Induced field will be the E naught minus E naught minus E will be E prime. Or if I write in terms of vector, I should write E is equal to, vector E is equal to E naught plus vector E prime. But then when I put the direction, it becomes E prime is equal to E naught minus E. Okay. So what is that going to be? E naught I have is 3.25 into 10 to the power of 4. Then minus E prime is 2.56 into 10 to the power of 4. Okay. So I get E prime to be 2.56 into, wait, 1 second. Sorry, here it is not, made a mistake. So E is not 2.56. How much is E? E is 6.9. So E is 6.9 into 10 to the power of 3. So the difference between these two will be 2.56 into 10 to the power of 4 Newton per coulomb. So you can find out what is the polarization field. This field is called the field because of polarization. Therefore, it is called the polarization field. Okay. Now, the next part of the question is, can you say how much was the charge induced on the two surfaces? Can you find out what is the charge induced on the two surfaces? We are not asking charge induced. You are just asked to find out sigma induced. Sigma induced. You know that E prime got created because of this sigma induced. So I can say E prime is equal to sigma induced divided by epsilon naught. Just as we had written for the metal, you remember what you wrote for E naught? E naught is sigma divided by epsilon naught. Like that, here you see these two induced charges will behave as if they are two sheets of charge. They will behave as if they are two sheets of charge. Sigma induced minus and sigma induced plus. Okay. Therefore, because of these two, there is a field in between. That field is going to be your E prime. That's going to be. Yeah, that's going to be E prime. So E prime, look at the direction, E prime is this. Okay, so you can get your E prime as sigma induced divided by epsilon naught, which is what the author has done here. And he gets the value of the induced charge. The induced charge density, he gets it as 2.27 10 to the power of minus 7 coulomb per meter square. Okay, now what I want you to do is, sorry. Sorry, one sec. Because of lack of space, I'm just losing my orientation. Okay, so from here, get sigma induced. Sigma induced is going to be equal to 2.27 into 10 to the power of minus 7 coulomb per meter square. Okay, now what I want you to do is guess and tell me whether sigma will be greater or sigma induced will be greater. What is sigma? What is sigma? Sigma was the charge on the two metal plates. What is sigma induced? Sigma induced is the induced charge on the surface of the dielectric. Which charge do you think is going to be greater? Yes, work, yeah. E naught you saw is greater than, E naught is greater than E prime. So from that you can conclude that sigma induced will be greater than, you can conclude that sigma will be greater than sigma induced. Yes or no? What is sigma? What is E naught? E naught is sigma by 2 epsilon naught. What is E prime? Sigma induced divided by epsilon naught. Okay, so the charge induced will be small. That's the reason why it is able to reduce the field only to a certain extent. It is not able to make the field inside zero like in the case of a metal. Now, based on this one problem, I can ask at least 10 MCQs in your examination. At least 10 MCQs can be created from just this one numerical. Okay, in that sense, it's quite an important concept. So with this, I am winding up. Any doubts you want to ask? I'll be sharing this by afternoon. I'll share this PPTs with you. Any doubts? So please understand that this concept is very, very important because for the next chapter, capacitors also, this chapter is going to be very important. Okay, so assuming that you are all not having any doubts, you have all understood everything, and you are all just sitting there because I forced you to come, I will now wind up the class.